Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Gottlieb with us today. Hey, Orr.
Hey.
How are you?
I'm very well. How are you?
I'm doing awesome on this July 22nd of 2022 as we shoot this. And it is cloudy and gray and overcast in Phoenix. And we're probably going to get one of our patented summer monsoons. So this is the rainy season in Phoenix. This is when we get our lightning, our thunderstorms, and all this kind of cool stuff. It's actually pretty awesome to see. And where are you located at, Orr?
At the moment, I'm back in my home country, Israel.
Oh, very cool. And where about in Israel?
Israel is hot as always.
Oh yeah,
I'm currently in Haifa. Haifa. Yeah.
Yep. Very cool. And I believe you have a position at Northwestern, yeah?
Yes, that's correct. I graduated last year from Tel Aviv University in Israel, and I started my postdoc in Northwestern a year ago, and now I'm finishing the first year of my postdoc out of the two that I have.
Very cool. Very cool. So we can call you Dr. Gottlieb. That's awesome. Very nice. Cool. And Orr, what do you like to do for research?
So I study relativistic high energy phenomena. So mostly jets, and specifically jets that produce gamma ray bursts. So gamma ray bursts are the most powerful explosions in the universe. And they can provide us a lot of cool stuff, and they can be seen from everywhere in the universe. So it's really cool to look at them.
Very cool. And speaking of very cool, let's go ahead and that'll lead us to this very awesome letter, actually. This is an APJ letter. It's open access, people. Go ahead and get it for free. Go grab it. On the Ejecta interaction in 3D GRMHD simulations of binary neutron star merger aftermath, and Orr, take us away.
Thank you. So yeah, this is a paper that we recently worked on. My collaborators are mostly in Northwestern. So we were working together with Serena and Teresita. These are PhD students in Northwestern. And also with Ari, who is a NASA fellow in Northwestern. Matthew Liske is the developer of the code that we used for this study. And Sasha Chekhovskoy is the one who's running the group, the professor in Northwestern. So, this is a study that we conducted several simulations of general relativistic magnetohydrodynamic simulations. So what we wanted to look into is what would be the outcome of different types of setups in these simulations. So maybe let me start with a little bit of background to this study. So neutron star mergers in general grabbed a lot of attention following the first detection of binary neutron stars GW7917. This is the first and so far only event from which we have a multi-messenger gravitational wave and electromagnetic signals. So there have been many studies, numerical, analytic, semi-analytic studies of the jet interaction with the debris from the neutron star merger. But specifically, there have been, roughly speaking, two types of studies, numerical studies of these systems. One was the study of the jet launching. So following the merger, we have the formation of a black hole. And if the black hole forms, then we have gas accreted to the black hole, and this gas that is accreted to the black hole can launch relativistic jets.
Cool.
On the other side of the spectrum, we have these jets that are flying far away from the side of the merger and ultimately produce emission. So these numerical studies can either focus on the jet birth or on the emission long time later. But it's very hard to look into both sides simultaneously in a self-consistent way.
Okay.
to connect the birth of the jet and the emission from the jet at the same time. So we have a self-consistent model that doesn't require us to assume anything about the jet launching.
Right, right. Good, good.
Yeah, so what we thought that we should try to do is, for the first time, to come up with a setup that allows us to explore and follow the jet for its entire evolution, from its birth by the black hole to orders of magnitude far away from the black hole until it emits the GRB.
Cool. Okay, I'm with you.
Yeah, so so that's what we did, and using the code Hammer developed by Matthew Liska, one of the co-authors of the paper, we set up about 10 different simulations with 10 different initial conditions, and we try to see whether we find any new physical phenomena that have not been observed before in simulations. And specifically here you can see in table 1 the different setups that we considered. So our parameters were motivated by this extraordinary event of GW7917. This is the only event that we have so far.
Might as well get it.
And it gives us it gives us quite a lot of information about this merger site. So we know a lot about the ejecta. We know the mass of the ejecta roughly. We know more or less about the density distribution of the ejecta. So this gives us quite a lot of information.
Yes.
We also know from observations what was the energy of the jet, and what was roughly the time that it took the jet to break out from the ejecta. So we can really place very good constraints on all of these parameters. However, because we want to see, and it's expected that these parameters will not be the same for each event, we want to vary the different parameters and see how they affect the outcome of this merger.
Okay.
So we looked into different types of density profiles of the ejecta from the merger. We looked into different types of magnetic fields in the disk that forms after the merger from the gas that is falling onto the black hole. We looked into different types of magnetic field strengths. And we saw how one changes the outcome that we get. So this was the basic idea. This was the motivation of our study, as the first study that does that. What we found is
let me ask one question here. What is we got two models here that have lots of dots in it, VBW and V. What is different about those?
All right. Yeah. So thank you for this question. It's actually, we also wanted to separate the effect of the interaction of the jet with the disks and the effect of the interaction of the jet with the wind from the ejecta. Sorry, the wind is the ejecta. So from the ejecta from the merger. So the models where we which we called V or VBW are models that are vacuum. So we have no ejecta in these models, and this way we can actually isolate the ejecta and see whether it is the ejecta that dictates the jet structure, or it's the interaction of the jet with the winds from the disk that sets the structure of the jet. So this is another test for us to understand better how the jet is escaping from the ejecta.
Okay, cool. Thank you.
So I think we can look into figure 1 maybe.
Sure. where
we show the different parameters at the black hole. So I think that the first panel here, it shows the accretion rate onto the black hole in the different models. And this shows us that all different models, they start with very high accretion
Yeah.
in the first 0.1 seconds or so. And
Mhm.
then it drops very fast, and
Yeah.
it stabilizes between 10 to the minus 3 to 10 to the minus 4 solar
Yes.
mass per second.
Mm-hmm. Okay.
So here we see differences, and these differences they originate in the different powers and different types of ejecta, but these differences don't seem to be very significant for the outcome of the simulation.
Yeah. Within an order.
I think that probably the most informative panel here would be maybe panel C, where we see the efficiency of the jet launching. So, so here we can actually ask how much of the gas that has been accreted onto the black hole converted to the jet power, whether it's an efficient process or it's inefficient process. And what we see here is that there are roughly two types of systems. One where the jet reaches efficiency of even more than unity, between 1 to 2. And this is essentially 100% efficiency. So that means that these jets are very efficient. All the mass is converted to jet power. And here we will have a steady, stable jets that are lasting for at least the duration of the simulation.
Cool.
So this would be all the ones that saturate at about between 1 to 2 in the efficiency. The other type of jets is the ones where you see here that are at some point falling below unity. These jets, so you can see the green that doesn't even reach 1. It falls very early on. And there is also the pinkish one that is also barely reaching a 1. And there is the brown one that is 1 for
a little bit.
Exactly. So the question is why one type we get to behave in such a way, and another type would behave in a different way.
Indeed.
And the question is essentially, what is the relation between the jet power and the ejecta? If the ejecta is having much stronger or more energetic power, then this would essentially choke the jet. It will not allow an efficient jet launching at the base of the jet. And then what would happen is that the efficiency of jet power would reduce, and ultimately it will shut the jet off. And this is what we see here when the efficiency drops. On the other hand, if the jet is very energetic, much more energetic than the run pressure of the infalling gas, the jet doesn't care about the ejector so much, right? So it's just flying away. Exactly. And then we will get very high efficiency at all times. We don't care about the ejecta. So this is the story really here. And then why some jets would be energetic and why others will not be energetic, this brings us to the initial conditions that we considered. So as I mentioned before, we explored the parameter space with different types of simulations. And for example, we see that different reasons can lead to this inefficient jet launching. One reason can be that the magnetic geometry in disk is toroidal rather than poloidal. Toroidal geometry is known to produce less efficient jets, weaker jets that will have much harder times to overcome the run pressure of the infalling gas from the simulation. So these weak jets cannot penetrate through the ejecta, and for that reason, they will fail. Another type is if we have a lot of bound mass in the ejecta, this bound mass of the ejecta is falling on the black hole. It's blocking the way for the jet because of the run pressure of the infalling gas, and for that reason, the jet will be choked again. And another reason could be, for example, that the magnetic strength of in the disk is just not strong enough, so the jet will not be strong enough to overcome. So it's all a question about what the initial conditions tell us about the ratio between the jet energetics and the ejected energetics.
Cool.
So this is all there is to it, really. And this can be translated when one multiply the efficiency in panel C in the accretion rate in panel A, we essentially get a panel D, which is the luminosity. So if the efficiency is about unity, all the mass is converted to luminosity to jet power. But if it's much less than unity, that only a small fraction of the accretion rate is converted to jet power. And then we get these very low luminosity jets that cannot penetrate through the ejecta. As we'll see, they will never break out from the ejecta for that reason.
Right. They get stuck.
Yeah.
Very cool.
So these are the conditions deep inside the system. But these conditions, once we understand them, we can already foresee what is going to happen later on when the jet tries to go farther away and eventually break out from the ejecta. So for that reason, as I mentioned, that we have this ratio of jet energetics and the ejecta energetics, and there is one quantity that we can actually formulate analytically and try to understand how it affects the outcome of the merger. And this is what is mentioned here in equation 4 as eta naught. So eta naught essentially tells us that it is the ratio between the jet luminosity and the ejecta isotropic equivalent energy, which is in the denominator, and the opening angle of the jet, and the time delay, which is TD. And the time delay is the time between the time of the merger and the time that the black hole formed or the jet was launched.
Yes.
And the reason why this equation includes TD is because the longer we wait, the more time the ejecta has to expand or the bound ejecta to be swollen by the black hole. So this will free the way for the jet to fly away.
Cool.
The shorter the time delay, the harder it is for the jet to overcome the very high densities close to the jet production site. So this equation was formulated previously by Udnakar and me in this GN21 paper. And we using this equation, we can say we have different types of outcomes. And this is what we studied in the second part of this paper.
Good. Okay.
So we can probably scroll down a little bit.
We'll scroll down. Got very cool renderings. Let's take a look.
Yeah.
Oh, very nice.
This is
wow.
So here we have the.
Wow. There's quite the morphology here. Very good.
So I think this figure tells the story.
Yeah.
Wow. Yeah. So we start with our setup is starting really with torus. This torus that is motivated by the observations of GW717. And this torus can launch these jets. And what you see in panel A is the torus in red, and these bipolar jets that are launched from the black hole deep inside this torus. And these jets start to propagate outside. And as they drill their way inside the ejecta, they spill some of the ejecta sideways to form a hot layer of shocked gas known as the cocoon, which is what you see here in green around the jet.
Yep.
So this is the first moments of the jet launching, and only 0.05 seconds after the formation of the black hole or the beginning of our simulation. And in panel B, you can see already the full structure of the jet as it built during its interaction with the ejecta. You see that the jet forms this complex structure with cocoons around it. And the color map, by the way, is the magnetization here. So you can see that the jet is highly magnetized, whereas the cocoon has lower magnetization because of mixing between the jet and the ejecta that is unmagnetized. So it reduces the magnetization in the cocoon. So this is the structure with which the jet escapes from the ejecta. Panel B is taken at the time that the jet escapes from the ejecta, and this will be the structure that had the emission been released at this point that the observer would see. And we see in GW17017 that this structure plays a very important role observationally, because if we understand the structure, we can place constraints on the system. We are not necessarily facing the jet. We may see the system from different viewing angles. And if we see different viewing angles, that means that we see different parts of this structure. And this is where the cocoon comes into play and tells us that whatever we see may tell the story of the early times of this building of the cocoon and the jet. So this structure is something that we find here for the first time following the self-consistent jet launching and interaction with the ejecta.
Good.
And in panel C, you can see how the structure looks after the jet and the cocoon already escaped from the ejecta that you can see here as a sphere in the middle. And the jet and the cocoon are just flying out, expanding sideways, roughly to an angle of 1 over the velocity of each, or the proper velocity of each. And this is why they look more extended compared to panel B. And finally, in panel D, we show another scenario, very different one. And this is something that is related to the other family of jets that are less luminous. So in panel D, what you see is the final structure of jets that never manage to break out from the ejecta. So this blue material that you see there is nothing but the cocoon. The jet formed the cocoon while it was inside the ejecta, but the jet never managed to escape from the ejecta. It left the cocoon as the only cursor, or the only survivor of this relativistic outflow. And the cocoon is the part that escapes from the ejecta, and this is the part that may or may not produce some electromagnetic signals that will be detected. So this is where we see for the first time that the difference deep inside the system close to the black hole affects also the observational signature of the systems. So in panel C, we will see a jet if we're facing the jet on axis, or we will see its cocoon off axis. Whereas in panel D, there is no jet. The entire outflow is expanding sub-relativistically, and what we will see is the cocoon. So, so this is the difference in the outcome of the two families. Now, we can actually go further and say there are not just two families, there are three families. So one family is the one that we see in panel C. One family is the one that we see in panel D. But the other family is one that will produce neither jet nor cocoon. And this is something that will produce essentially no outflows at all that we can detect. So in these systems, the only thing that we can detect would be the emission from the ejecta itself, known as the kilonova. But there will be no signs of relativistic outflows, no jets, no cocoons. And this is the difference between the four. So if we actually go back to figure 1.
That's why I was sliding up.
So in figure 1, we saw 4 types of jets that they don't have efficiency of 100% at late times in panel C. And this are having in common the thing that they don't have jets, but they're not exactly the same. The ones that can sustain high efficiency for longer, for example, the brown line,
Sure.
they will have enough energy to let the jet run an sufficiently energetic cocoon, so the cocoon will have velocity that is faster than the velocity of the ejecta, so the cocoon can finally escape.
Got it.
The weaker ones, for example, the green one,
Okay.
The jet is so weak
Got
that the cocoon that it energizes is also going to be so weak that the cocoon will propagate so slow that it will never catch up with the front of the ejecta to break out from the ejecta.
Yes.
In that case, we will not have any evidence for the existence of jets in such systems.
Yes. Okay.
So we actually have 3 types of families, and this is something that we see here.
Got it. Very good. Let's go back to there. Got it. Okay. Very good.
Yeah. So finally, we can look at the next figure, where we can say whether we can say something interesting about the jets themselves. So since this is the first study that looks into the self-consistent launching of jets and their interaction with the ejecta, this is the first opportunity for us as researchers to learn how the interaction with the ejecta affects the magnetization, for example, in the jet.
Okay.
So jets are known to be, or at least considered to be, launched through Blandford-Znayak mechanism, which tells us that the jet starts highly magnetized, pointing flux driven outflow.
Yes.
And the question is, what happens to this magnetization when the jet is emitting its radiation? So the source, the powering mechanism of GRBs is something that is poorly understood, and we don't know whether this emission mechanism is driven by some synchrotron emission, by photospheric emission, by magnetic reconnection. So understanding what is the magnetization that the jet can retain at the time that it emits the radiation can help us understanding better what is the emission mechanism of such jets. And this type of simulations is our way to study this. And this is, again, required that the jet will be both launched sort of consistently and interact with the ejecta. This is something that we can use for this simulation that does this for the first time. So what we see here in the first panel is the magnetization profile. If we focus on the solid blue line, we see that the jet starts at high magnetization, and over time, the magnetization drops. And towards the end, the magnetization is subdominant. It's between 0.1 to about 1. Another interesting thing to look into is to understand why the magnetization is falling. And what we see here is, if we look at the black line, which is U infinity, this is the maximal velocity that the jet can reach. And seeing that this is consistent tells us that there is efficient conversion of magnetic energy to kinetic energy. So that tells us that we understand where this magnetic energy is going to. It goes to acceleration of the jet. That it means that there is no loss of energy, for example, to mixing with the gas, with the ejecta, and the jet can retain most of its energy and is just accelerating.
Cool.
Now, having this magnetization tells us that it's nor hydrodynamic jets, neither hydrodynamic jets nor magnetized jets that have been previously considered in analytic studies. So the simplified model will tell us the jet can be emitting GRBs through magnetic reconnection. This is purely magnetized jets, or it can be emitting GRBs through photospheric emission, which is purely hydrodynamic jets. But
Yes.
what we actually see here is that the picture is much more complex,
Yeah.
and the jet is partly magnetized, partly unmagnetized, and all physical processes should be considered when we're looking at the emission mechanism of GRBs.
Yes.
And this is the same behavior as we see in the other panels, in the other models as well. We see that the jet, as long as the jet is successfully breaking out from the ejecta, its magnetization is somewhere between 0.1 and 1. And this magnetization it has a lot of magnetic energy, but it also has a lot of non-magnetic energy. And this is something interesting that we derive for the first time. And here you can actually look into other types of model, the green and the brown ones, where there is a cocoon, but the jet is choked inside the ejecta. These are the weak jet models that produce cocoons. And you can see that the magnetization here is much, much smaller. And the reason, as I mentioned before, is that the cocoon, unlike the jet, is forming as the jet is shocking the ejecta.
Yeah.
Now, this mixing between the jet and the ejecta reduces the magnetization, and for that reason, the cocoon comes out as very weakly magnetized, and essentially the magnetic energy in the cocoon is negligible. So these are the results that we find here, and in panel, I think, in figure 4, we can probably focus on another aspect of our simulation.
I'll go there.
Where we see the structure, the angular structure of the jet. As I mentioned, the structure of the jet is very important when we see binary neutron star mergers, especially in the phase of the afterglow, which is the later interaction of the jet and the cocoon with the interstellar medium. The reason is in GW7817, for example, we saw it from the side, and the observational imprint of the structure is going to be shown in the afterglow. So this is why we looked into the structure of the jet. And what we find here is interesting. We see two types of structures in panel A. One shows us a flat distribution in the core of the jet, in the say below 0.08 radian or so.
Yeah, fairly.
And then we have a power law that is falling from there all the way, which is the cocoon. And what is surprising here is that you can see that all models that produce jets, they have the same type of structure.
Interesting.
Their normalization may be different.
Sure, up and down.
But the structure is essentially the same. And that tells us, and not only is it the same, it's even the same as in the model without ejecta, in V model.
Yeah, right. The gray one.
And that tells us that the ejecta doesn't play a very important role for such jets. And actually, this is the disk that is forming or shaping the structure of the jet.
Okay.
In the other type of the brown and the green jets, or not jets, the models, we don't have jets, we have cocoons, and these cocoons, because they mix with the material, they form a more isotropic outflow, and for that reason we see less energy in the core of the jet because there is no jet, and more energy outside because the flow is quasi-isotropic. So even here we see, at least with these two models, something that is very similar.
Yeah, other than up and down normalization.
Yeah.
Cool.
So this could be interesting, and in panel B we see the distribution in the velocity or the radial distribution, which is how much energy we have in the slow parts and in the fast parts. So these type of models can help us understand better once we have in LIGO O4 run that is expected in about half a year to start, we will be able to maybe place constraints on the parameters of the system from observations. In panel C, we see what I mentioned earlier, is that how much magnetic energy out of the total energy we have in different models. And it shows that in the models where there is a jet, a lot of energy is between 0.1 to 1 in the magnetization. Now, the magnetization is the ratio of the magnetic energy to thermal energy.
Yes.
And that tells us that in some models, we have more than 10% of the energy
way more
in sigma, the magnetization that is above 0.2 or 0.3. So that's enough energy to give us emission through magnetic processes.
Nice.
In the blue and the green, again, not surprisingly,
they don't.
Exactly. We don't have much
to say there.
Yeah.
And then we got luminosities. There we go.
Yeah, and the luminosities.
Okay.
These are just the luminosity that we see, just to look at how consistent these jets. So with observations. So previously, in simulations, you launch a jet by hand. You put the luminosity that you want, the duration of the engine that you want, just to fit the observations. But here, we have no control of that. We put magnetic field, we put a torus, and we get a jet. We don't know how this jet is going to look like and whether it's consistent with observations.
Fair enough.
And what we see here, which is very reassuring, is that our jets are typically about a fraction of a second long, which is what we expect in short GRBs.
Yeah.
And their luminosity is also about 10 to the 51 erg per second or so, which is also, although on the a little bit high end of the distribution, still consistent with what we expect.
Yeah, fair enough. Very good.
Yeah, so that tells us that it's possible that this type of jets is what we actually see in nature.
Very cool, very cool. Where's that gray one?
Okay. Yeah, so
pink one. Okay, so I was just following something. I'm good.
Yeah.
Cool.
So I think this is a study that can motivate future studies to look into the more complete picture now that we have the machinery and we have the numerical models that allow us to do such analysis. We will be able to come more prepared towards future runs of such events, of LIGO, and to detect such events.
Yeah.
In this paper, we also try to place some constraints on what should be the typical ejecta mass that will allow a successful jet for typical jet luminosity and so forth. And what we actually find is that a large fraction of these events, if we take the average jet luminosity and we take the what is considered to be typical ejecta mass, is that a large fraction of these systems will not, or is likely not produce a successful jet that is breaking out, but the jet will be choked. And this will be interesting. Of course, we haven't detected such systems, but maybe in the next run, we will be able to look into such type of systems that don't produce jets, but they produce cocoon or produce neither one of which. And this is something that we would definitely want to look into in the future.
Right. Very cool. Very cool. Nice. Or thank you so much for walking us through this very lovely APJ letter. Thank you.
Thank you.
That was great. Let me ask one question before I ask my second question. So what's a typical runtime for these? Are these like, do these run in 1 second? Do they run in 1 minute? Do these take 3 months of runtime? What is a typical one of these GRMHD runs take?
So that's That's a good question. So these specific simulations, they run, each of the simulations run about a couple of weeks.
Okay.
So we run them on supercomputers, and because we use GPU, it accelerates the integration time substantially, and this allows us to do such calculations just in a couple of weeks. Otherwise, it could have been a couple of months or even more than that.
Yeah. Okay. So given that, and you did mention it a couple times, right? We got 04 coming up, and I'm sure your computers are not sitting there idle. And so let me ask the question of where do we go from here in the future? Do we examine a larger class of objects? Do we bear down on the resolution or the time resolution? Do we do just where do we go over the next couple of years with these kind of simulations in relative to what the observations will be?
So that's a very good question. I'm not sure that there is one answer, but
I'm sure there isn't.
Yeah. So the way I see it, so first of all, of course, we have to look to see what we're going to find in this in 04, maybe in 05. And of course be open and open-minded and see maybe we need to change the way that we think about these systems. But until then, I think that we can improve the numerical setups. We're now working on including neutrinos. Our simulations right now, they are only general relativistic congenital hydrodynamic simulations. We have no neutrinos. And once we include neutrinos, especially in neutron star mergers, they're expected to take a significant role in the early times of the merger when the densities are still high, and they may affect the dynamics that we find. So one thing that we're working on right now is to include neutrinos in our scheme.
So neutrinos basically act as an energy sink, right? Because they free stream.
Right.
Yeah.
Right.
Okay. So thermal neutrino production.
Right.
Okay.
And this is something that we definitely want to see how it affects our results. Maybe we can learn something about neutrinos if we can say something smart about what we find with and without neutrinos. And another thing that, as far as I know, has not been explored in this type of simulations is the merger of black hole neutron stars. So black hole neutron star merger is something that we haven't detected with gravitational waves and electromagnetic emission, if there is one. There is, I am not sure if it's confirmed, but there is one event with black hole neutron star gravitational waves. But such simulations is something that we can do because there are numerical relativity simulations that merge black hole and neutron stars, and we can take these simulations and we can remap them into our setup and just let them evolve and see what we get. And there are currently no predictions of how this is going to look like. And this is something that we're working on now. It's very likely and possibly that in 04, we will detect such system. The rate of these events is not very small. So yes, hopefully we can detect these systems. And if we come prepared, we can test our models in a better way.
Well, we always like to be prepared.
Yeah. So this is definitely something to look into. Yeah.
Yeah. Well, I look forward to, I think the next year or two is going to be pretty exciting on this field. So I really look forward to it. And I look forward to your next article as well. So very cool. So, Or, thank you so much once again for chatting and talking about your awesome APJ letter. And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye-bye.